So, what is the objective of engineering processes? Okay. Most engineering processes one of the important objectives is to convert raw materials to useful products. That conversion has to be done in an efficient, economical, safe and environmentally friendly manner. Just because you know the chemistry or the process for conversion, conversions are basically either physical or chemical processes. Physical processes involve things like heating, cooling, melting, freezing, subliming, changing phases and so on. Chemical processes involve chemical conversions of a raw material to a finished product. In all of these processes, you have to supply the material, maintain the conditions for the reaction to take place, and then take out the finished products. You may have to supply heat or remove heat. These can be done in the laboratory, but when you go out up to try to produce it in an efficient, economical, safe and environmentally friendly manner, in order to take advantage of economies of scale and efficiency, these are done in large scale processes. Okay. An example of a process would be, for example, a reactor. Okay, where you have some inlet where some material comes in, and there is an outlet where the material comes out. Okay, this is the product, reactant. Okay. You might have a stirrer, for example, to stir this vessel, and if it is a heterogeneous catalysis reaction, you would have catalyst particles here, okay, which are used for catalyzing the reaction. Okay. Now, just because you put in the reactants and take out the products, it does not mean you will get the desired result. Okay. Because what has to happen is that the reaction has to take place at the microscopic level, either by mixing the fluid or through reactions on the catalyst surface. Okay. And if I look at the catalyst surface, okay, and I blow it up, okay, if I have a reaction of the kind A goes to B, okay, there could be multiple reactants, multiple products. In all cases, it is necessary that the reactant has to reach this surface, okay, and react over there. It is not sufficient if the reactant reaches the surface, the product also has to come out of the surface, because if the product stays there, there is no place for more reactant to go. Okay. And you also have other conditions. Okay. Either heat energy has to be provided at the surface if it is an endothermic reaction, or heat energy has to be removed from the surface if it is an exothermic reaction. Okay. Because if you do not provide heat, the temperature will decrease and the reaction efficiency will decrease. If you do provide too much heat and the reaction is exothermic, you could have hot spots. These processes at the microscopic level are what determine the macroscopic efficiency of the process, and it is essential to understand these in order to be able to design process equipment. What is it that determines this transport at this microscopic level? There are two mechanisms. One is convection. Okay. For example, you have a stirrer in here so that it can convect the fluid around and mix the fluid. Okay. Convection is transport along with the fluid. As the fluid moves, it carries along with it whatever materials is within. However, the fluid convection is only along the surface. Okay. There is no fluid motion perpendicular to the surface. Therefore, transport perpendicular to the surface has to be due to diffusion. In this series of lectures, we will look at what is it that determines convection and diffusion. What are the basic equations for convection and diffusion? How can we simplify them when either convection is dominant or diffusion is dominant? And how can we solve them? And then get correlations of the kind that will be used for process design. Specifically, how does the physics at the microscopic level determine performance at the macroscopic level, okay, for fluid systems which contain reaction and diffusion. We will start at the very simple level, dimensional analysis, proceed little by little until we go to a fairly advanced level where we will actually be able to derive correlations for convection dominated flows, diffusion dominated flows, and we will derive many of the empirical correlations that are actually used for designing such systems. That is the objective of this course. A fundamental physical understanding of what determines transport at the local level, and how can we use that understanding in order to derive the kinds of correlations that are used for designing these processes. So, if you are interested in that, kindly come and join this course. We will see you there.